Hello, and welcome. My name is Michael Brand. Welcome to my final project presentation. If during this recording there's any kind of a mess up, I apologize. This is my third time trying to record this video. I am not having fun with this recording software. It also only limits me to 15 minutes, so I'm going to have to try to get through this quick. Today we're going to be talking about peer-to-peer processor sharing. Now, what is that? Well, as we all are already aware, there are plenty of server farms out there that are able to take in requests. They distribute those requests among a whole series of servers, and by distributing those process requests accordingly, they can make sure that no one server is massively overburdened while others simply sit idle. They can distribute the load and give an even work distribution. So, the thing about that, though, is that networks come in all shapes and sizes. Yes, there are server farms, but there's also LAN parties. There's this smaller networks, such as the Citadel network, even, or maybe just some library somewhere. And there's no reason really that we can't use this kind of load distribution. Well, I mean, there's security issues, but we'll get to that in a minute. That we can't use this kind of load distribution in order to even out the load that is being distributed among those machines. So, let's talk for a minute about resource sharing. So, peer-to-peer file sharing has been around for quite a long time. It's been around since the days of Napster, and even before that. And it allows machines to share one another's resources, but that really was always specific to file sharing. The implementation that I have in mind refers more to processor power, sharing processor power as a resource instead of memory, and that actually seems like it would be a lot more efficient, just because file sharing, a file is something that's going to end up being persistent in memory. It's going to continue to use that memory for as long as that file needs to be shared. But processor power and the needs, therefore, are going to shift with the wind. One minute, one processor or one machine is going to need as much processor power as it can get. The next minute, maybe its friend next door is the one that needs some help. So, this seems like it would actually be a lot more effective. Now, we talked about process distribution and load balancing with a server farm. Now, most server farms are going to depend upon a load balancer. As we see here, the load balancer receives requests that come in, it sees its server pool, and it decides which server is going to receive that request. Our implementation is just going to take this exact same concept and it's going to try to bring it down to a much smaller scale. Also, we're going to see if we can decentralize it. Simply because, yeah, the more decentralized, just the more elegant everything tends to be, in my experience. Alright, so processor sharing policies and load balancing policies. Now, the implementation that I've just suggested is way too large to really be encompassed in a single project. I've tried, it just was too much. There's a little bit of networking that goes on, there's a little bit of processor sharing concerns, and there's also some security in there. But that's just too much, so here we're going to focus specifically on processor sharing policies and on load balancing policies that we believe would be optimal for such an arrangement. Later work is going to focus on optimizing other aspects of the implementation that we just discussed, so network topology, security, etc. Alright, related work, load balancing. So there's plenty of load balancing policies out there that we can find. A lot of them very much resemble processor queuing policies, actually. But we've got, for example, just to name a few that stood out to me as being helpful to understand what was going on. Round robin is one where the load balancer is going to distribute jobs one at a time to each machine in the server farm in sequence. This is really great for larger server farms because it means that the load server doesn't actually have to keep track of hardly anything. It just needs to know how many servers are in the farm and where it is in its sequence. That's all that it needs to keep track of. But it's not quite as efficient as some of these others. For smaller server farms, we have the join shortest queue policy. In this one, the load balancer actually keeps track of all of these servers in the server farm and exactly just how full their queues are. And every time it gets a request, it's going to check on that, and it's going to issue that request out to the server that happens to be in its farm that has the shortest queue presently. And lastly, we have the shortest queue out of D. By the way, the shortest queue policy is optimal efficiency. Like, you will have the best load balancing using that. But it's not something that really scales well. Once you get up to like 100,000 servers or some odd, it's just too much to keep track of. Now, shortest queue out of D is one that kind of becomes the best of both worlds with these. Instead of taking a census of all of the machines in the server farm like join shortest queue does, we simply survey some number D of randomly chosen machines, and it's going to issue the process request to the one that has the shortest queue out of those that we've surveyed. It's pretty close to optimal efficiency, even if we're only surveying 2 machines, and it is a whole lot more scalable than the join shortest queue strategy. Alright, now in terms of processor sharing. Processor sharing is something that happens inside of one single machine. Process sharing is something that happens inside of one single machine, but process sharing was something that was designed way back in the olden days when we had like 20 people all trying to use the exact same computer at the exact same time, and basically everybody, we had, time sharing. Everybody kind of had to take turns using the processor to get their work done. It does still exist today, just to a much lesser extent. Usually whenever it is utilized, there are different classes of processes that exist. For example, on the Citadel's network, we might have different classes for an system admin. We might have a different class for students, for a staff member, or for a guest. Basically, whoever creates the process might have a different class associated with them. And those classes all have their own processes existing on separate queues, that are going to be considered by the server differently. Now, within each queue, they each have their own policies, maybe first in, first out, maybe you're going to do shortest job first, etc. But we're just talking about the policy we use to select from amongst the queues. So we have the generalized processor sharing policy, in which each queue is given its own weights to determine the probability of it being chosen relative to its peers. We see right here, each of these different queues has its own weight, W1, W2, WK. The server is going to make a calculation based upon that, and it's going to determine which of those queues is going to be served next. Now, if one of those queues is empty, its weight then is going to be distributed proportionally to either of the other 2. Yeah, it's very efficient because only a single calculation ends up being used. Now, with the hierarchical GPS, it's a little less efficient, but basically what this does is it uses preset probabilities, and if the first class uses preset probabilities, and it makes determinations one at a time. So first it's going to make this determination R. It's going to say, okay, am I going to select class D, or am I not going to select class D? There's 20% chance we're going to select class D, 80% chance we're not, and if we don't, then we move on to the next decision. Because of the way that works hierarchically, if, let's say, queue A is empty, rather than it distributing that 5/16 probability to both of the other queues, it's only going to give that the rest of that over to queue Bravo. Queue D still has only a 20% chance of being selected. Alright, now, how would we implement something like this? Well, our hypothesis is going to be that a network of machines capable of sharing processes while under duress is going to produce lower overall sojourn time and higher throughput than one which cannot. Many instances are going to be created on the Amazon Web Services EC2 to form a mesh network. The machines are going to be arranged in a chord structured decentralized ad hoc network. And chord networks work based on a distributed hash table that is going to be present on each machine. Because it has that distributed hash table, we're going to have each individual machine going to perform the shortest queue among D type survey, and it's going to be evaluating all the machines that it has on its own distributed hash table. so it's going to be very scalable that way. And it's going to be selecting the one with the smallest queue from among those machines. Each machine is going to be using the hierarchical generalized processing sharing queuing policy, as well as the first in, first out policy to organize the process within each queue. We went with first in, first out because it makes it a lot easier to track sojourn time. All nodes will randomly generate expensive tasks with a probability modeled upon the Markov modulated Poisson processes. Remember, we're assuming that each of the machines is going to be generating its own tasks rather than simply receiving tasks from outside the network that need to be executed like it would be in a server farm. Now, when the CPU utilization on any one machine exceeds 90%, we could change that threshold if we wanted, but 90% seemed like a good marker for me. And when it exceeds 90%, then the processor will begin issuing unserved processes to neighboring machines on the network. Alright, now what kind of variables are we going to be controlling for here? Well, we want to make sure that all nodes that are randomly generating these expensive tasks are doing so with the exact same Poisson modulated process, and that the probabilities are the same for each node on the network. It's also going to make sure that every processor on that network is going to have equal capabilities. We don't want any one of them having vastly faster processing capabilities than the others, because that's just going to make everything more difficult to track. Each decision made in the hierarchical decision-making tree of the hierarchical generalized processor sharing policy is going to have a 50-50 probability. Just makes everything easier to calculate. The four classes that are going to exist are, as we stated earlier, we've got admin, staff, student, and guest. Results and conclusions. Oh, and by the way, each of the nodes, the assortment of nodes that we're going to have is going to be evenly distributed among these as well. Yes, results and conclusions are going to be based upon sojourn time and throughput. Those are going to be our two key metrics. Sojourn time is the total amount of time that an object spends in a system before being transmitted. So in this case, it's going to be the process itself. Throughput measures the units of information a system can process in a given amount of time. This information is going to be broken down by class, so we're going to want to make sure how the different classes are affected by this setup. And also we're going to have two separate experiments, one in which we have this policy, this 90% threshold at which the process begins issuing unserved processes to neighboring machines, and another experiment in which it does not have this policy, and we're going to measure and compare the sojourn time and throughput on each of these networks. Now, future work. We did talk about how we had to basically limit the scope of this project. But future work, we would want to consider different machine capabilities. Cord is an ad hoc network. People tend to come and go. Maybe the different machines on your network have wildly different processing capabilities, and we want to make sure that perhaps maybe it would be better to give a machine that has twice the processing capability twice the queue length, or twice the tasks. We want to possibly use Gaussian processes to model traffic instead of the Markov modulated Poisson process. We also want to consider security issues. That's going to be a big one. Not only are we exposing our data and our processes to other machines, we are also exposing our processor to the processes that other machines expect us to run. So that's going to be a big deal. We can also explore other network topologies other than simply Cord. Maybe we want to go something that is a little more centralized, for example, or maybe even something that's a little more unstructured. That's a possibility as well. And we also want to consider expanding outside of the existing network. As long as we can get the security issue addressed, it might make more sense to leverage processing power on other machines. We don't want to create a botnet per se, but it would be nice to be able to go and make use of all that processing power. I have 20 seconds left on this recording, but I hope that you have enjoyed my presentation. I definitely enjoyed working on this project. Thank you for an awesome semester.